So this is session 27A of our course on mathematical methods for signal processing. And of course, there are 100 things that I would like to squeeze into this last lecture. I probably will continue to produce a few units and upload them to YouTube. So if you have questions, contact me and I might be able to answer it. Now, we are going to summarize a few facts that we have learned in this course. The first thing that I would like to tell you is that for people working in Fourier analysis, they are either acquainted with a huge variety of function spaces, they are specializing in multi-parameter function spaces, they are using weighted spaces, they're using anisotropic spaces, and it's what I call a zoo of Banach spaces or even topological vector spaces. There are even things which are more than temper distributions, so people call them ultra distributions. But the point of my presentation was essentially to do a fast path to what I call the Banach-Gelfand triple. The pair of Banach spaces S0 and its dual S0 prime, what I call the space of mild distributions, with L2 in the middle. So in this big picture, you see it, this is S0 prime. Inside you have the nice circle, which is S0, and L2 is right in between. Now, what I mean by in between, I mean by a reflection more or less along the unit circle. So the L2 is self-dual. All the linear functionals are given by elements of the vector space itself by scalar product. And this is the continuous analog of what you know from linear algebra. Dual space, all possible linear functionals on Rn are all the linear mappings from Rn to R1, which are exactly the 1 times n matrices. And you would say, oh yes, the row space of length n is the dual space of the column space. And if you see it in this way, it looks very artificial. Why make a distinction between the rows and columns? It's much more natural here, where you have the descent function. The good thing is you can embed the descent function into the bigger space. So whenever you have a space which is not too big, it will be embedded into the big space. And by not too big, I mean not something like L1. L1, you would say, has a dual space, which people call an infinity, or the bounded continuous functions if you take the continuous part in it. But there are integrable functions which are not bounded, and there are bounded functions which are not integrable. So this is not nice. You see it sticks out of L2. But once you're inside in L2, you have smaller spaces. Inside of L2 means dual spaces which are larger. And so you have this triple situation here. Now, if you are interested in temper distributions, you start with the even smaller space, this short space, rapidly decreasing functions. So more or less I have explained now this picture. I will not have time, probably, I'm afraid, to talk about the fractional Fourier transform, which in my picture would be a rotation by a general angle, whereas the Fourier transform is 90 degrees. There are other spaces, including the Wiener algebra, which I have depicted here. Or if you put everything together, you have pictures like this. Or you can take the construction of amalgams that we have used. We have used this space, local C0 global, this one, the smallest guy in the family, local continuous function, global L1. And we have put our S0 inside by taking only things which are local in the Fourier algebra, global L1. But there are many other such spaces where you replace the local and the global norm by general parameters. So L2 is local L2, global L2. Otherwise you have, or L1 is local L1, global L1, but you can have local L2, global C0, local L2, global L1, and all these things. And if you take these pictures, and we have normalized them appropriately, and you try to see whether the Fourier transform maps one of these spaces in the other space, then you find out that you can reflect it by duality. So we have seen L1 is going into C0. Now the Wiener algebra is going into this space, local Fourier algebra, global C0, you can take this space, then you're ending up here, and you can take this space and you're ending up here. So it's Fourier transform of the small guys, which are in the right lower end, are going into the bigger end or so. So you see these pictures are intuitive. Of course, they are made such that existing results are valid and just are made plausible or visualized by these statements. So, but sometimes I'm asking myself by systematic ways, is it plausible that something is true? For example, that for any fractional Fourier transform for a fixed LP space, I can say something, and then I draw my pictures and I get actually quite reasonable assumptions, which then have to be proved or disproved or so on. Now, the goal of all this is to show that even if you start from scratch, so from linear algebra, basic functional analysis, and Riemann integrals, you can get to this triple. We have done all this all the way. And so essentially the question is, what can you do with these things? Now there's a very long list. Because I will not have time, I mentioned we could do generalized stochastic processes, for example. Now, we have seen that a generalized function or distribution is something where you don't have definite point values at a given time, but kind of probabilities of, or you have average values over certain times. Now, generalized or a stochastic process means that you don't get a fixed number, but you're having a random distribution. So think of a discrete stochastic process as something where you're throwing a dice or a coin or whatever at each position. So instead of saying the value at this point is something, you only know the probability of getting something at this point is something. Now, if you think of weather prediction or any kind of forecast based on vague data, then you would say, well, what I know is only an average. Probably in the morning in this area, in the interior of the town, it will be a little bit warmer than on the countryside. Probably in the afternoon, let's say between 3 and 4 in the afternoon, it will be a little bit warmer and it will be more windy or so. So actually many data sets are kind of examples of generalized stochastic processes. So it's in a way not fancy mathematical object generalizing the true and valid functions, but it's more realistic model of what we have to do. I cannot do it, but you can imagine what the stochastic process is. It's a mapping from a zero, not into the one-dimensional complex numbers, but in the Hilbert space, which is arising from probability. What is the Fourier transform of a generalized stochastic process? Well, this is just, instead of applying this operator to a test function, you are applying it to the Fourier transform of the test function. So in this way, you get a very simple-minded approach to spectral representation of a stochastic process, which in our terminology is nothing else but recovering the stochastic process from its Fourier transform. I mention it because you might be interested in such things or might see this later on. The theory of stochastic processes is usually quite involved and even more technical than what we have here. But in the PhD thesis and before in the master thesis of my student Wolfgang Hörmann, already many years ago, and also Bernard Cavil have picked up this aspect of stochastic processes. And I think it's much more natural and much more intuitive. So recall we have the space S0, which is a space of functions which are absolutely convergent when you cut them into pieces. You have to do it by smooth Pupo, maybe a trapezoidal would be good enough, or triangular function. So you're inside the Fourier algebra, but you're also inside of L1 due to the atomic characterization. In the dual space, we realize that it's not dense. You can find that S0 prime is exactly the space of all the things, you can say temper distributions, which have a bounded spectrogram. So it's possible to define the spectrogram, of course, of an element of S0 prime, and it's very easy to find out that it is a bounded function. This is by saying, well, what is the spectrogram of a function? Well, you correlate the function with the time frequency shifts of your atom. So we know that we can replace an ordinary atom by the Gauss function by any other atom from S0. So let's take the Gauss function. And so what does it mean to produce a Gaussian spectrogram of a distribution? Well, we are taking scalar products, or we apply the distributions to the time frequency shifts of our Gaussian. This can be done quite conveniently. And at the very beginning, I was showing you a live spectrogram. I didn't have the data in the sense of the point-wise values of my voice. This was really a microphone recording it, but we can correlate it. We can take averages against pure, or correlate with the pure frequencies, which are done in a discrete way. And we get pictures. Well, we get pixel images, but of course they are could be viewed as approximations to the continuous spectrogram, very much as the results of your digital camera are viewed as approximations to the continuous world. And one shouldn't overdo it, because at the end, even the image, you could not go to the level of atoms and subatomic things. That wouldn't be a picture anymore. So it's all these things allow you to discuss things very much like real numbers. Pi is thought of an infinite decimal expression, but in reality, it's just an arbitrary long approximation. And depending on your needs, or what on your area of resolution that you need for your device, for a pixel image, or for your ear, for your eyes, for your sensing system, you're doing some approximation. Now, whereas we have in this big world, I've told you already, we have the discrete periodic things. If you do a Fourier transform in the abstract sense of a discrete periodic thing, you get a periodic discrete, but you can relabel it. So you'll stay within the discrete periodic vectors, and you're getting a copy of the DFT mapping, which is just the only defined inside of the big world. What I want to do next is a little bit explaining how you relate one to the other. So we have already seen that S0 is weak star dense in S0 prime. What was the idea? We should, maybe I try to change to another folder. Give you a new window. I hope I find the right one. Yeah. So let me see. This is not the right one. Just have seen this. Yeah, this is the right one. If you are giving me a typical object which is not in any of the small spaces, like a Dirac comb, and of course this is one of the very important things, then you would say it has two deficiencies. And the point of view of local and global properties is quite good. So you would say it's not decaying and it's not smooth because it's spiky. I mean, I represent here in discrete way the Dirac measures by unit vectors. Now, how do you improve it? How do you approximate it by something which is a good test function? Well, you're producing a finite collection of shifted Gaussians. And there are two ways of doing it. And what I was suggesting here is to first multiply it down, to first smooth it by convolving the Dirac comb with a narrow Dirac-like Gauss function, and then multiplying with the plateau function, which cuts off at infinity. You see the effect here on the Fourier transform side. Of course, you can also do it in the opposite way, because you could argue that multiplying these Gauss functions with a decaying function, they're not strictly Gaussians. So you might prefer to first multiply these Dirac measures. So you get a Dirac comb with weights, and then you convolve with Gaussians. Then you would really have shifted Gaussians with variable amplitude. And if you would look at the spectrogram of these things, they are from the dense subspace, but they would look at larger and larger domains over long and longer intervals because the plateau functions are getting richer. and in more and more frequencies, very much like the Dirac comb. Clearly, this Gauss function corresponds to a slowly decaying Gauss function on the Fourier transform side. So actually, this smearing out was a localization on the Fourier transform side, followed by localization on the time side. But of course, you could do it in the opposite order. And that was what I was doing here. I could say I'm doing a smearing first in the time direction, and then I'm going to the localizing, which is I'm doing a smearing in the frequency direction. So here you have something which is very spiky and a little bit broader here, but that's not important. Okay, let me take a quick look. Yeah, there's another thing which I would like to discuss next a little bit, sorry. That's the approximation of elements from the nice world, so from S0, by discrete objects. And so it is very natural, and it arises as a natural question. Yeah, we have the first thing which I should mention is, of course, if you're giving me a general distribution, then you could ask for approximating it by a discrete signal. Now we have seen at the very beginning of the course that you can use the discretization operator to achieve such a replacement of a bounded measure by bounded discrete measure. So what was the trick? We were verifying the spline approximation of the given function in C0 approximates the function. So this is the harmless fact that if you have a nice function in C0, or even in the bounded, uniformly bounded continuous functions, if you sample it on a fine grid and you do piecewise linear interpolation, then you will see at the end everything in an epsilon strip around the true function. Well, with the sup norm, this is actually what you use when you plot data from, using sampling values in MATLAB. So you're having a continuous formula, you're looking at the lattice points, you're evaluating it, and MATLAB is drawing, if you don't have other alternative commands, a piecewise linear interpolation, and you make it dense enough, and it looks really perfectly continuous. So what's not so obvious, and actually part of the paper that we cite here, is that you can do the same thing in S0. So you can argue, well, S0 is a subspace of C0, so it's no surprise. Yes, it's no surprise that you have uniform convergence, or if you want L1 convergence, which is not far from the argument that the functions in S0 are Riemann integrable. But if you're taking this quite sensible S0 norm actually defined in a more complicated way, you really have to do something. And it may be worthwhile to look for a more simple proof, but it's important, an important fact that is valid. So the function space is well enough smaller so that the more sensitive request that we have is still valid. And now just instead of taking the duality pair S0, C0 bounded measures, we take S0, S0 prime, and therefore we have this for free. It's just a one-line proof. Now, what I want to demonstrate next is that if you do this piecewise linear interpolation and you do it more and more refined, then you can have convergence. So it's more or less a more explicit way of doing this spline approximation theory. What is the spline approximation operator? You're sampling, so I'm taking f, a sample at the rate a, and then I compress my triangular function in such a way that the width of this is just the a. So dB of delta is just saying I'm taking a triangular function which is supported on minus a plus a, and it takes the value 1, of course, at the origin. So if you are doing this combination of operations, it's a discrete measure here, convolved with a nice function actually in S0, and therefore it's fine if it's in S0. And so this is another formulation of exactly the same thing for the special case that the psi family is coming from triangular function, and this proof is actually working in the same way. Now, I would like to mention it because it's a way to understand why it's realistic to hope that you can do it. by saying, well, what we should rewrite everything, I mean, we have the f, but this is the interesting expression. So the procedure, you're sampling, and then you're putting small triangular functions. And I would like to say, no, instead of compressing without changing the amplitude, I would like to compress the triangular function to in the L1 preserving way. And it turns out, and it's a very nice fact, that you can do the same thing with the dB. So of course we have to use this duality of the dilation with the, which we know from C0, and the area preserving stretching operator here. What was the idea? That if you want to know what the stretching of a measure is, you applied a stretched measure to f is the same as the original measure applied to the dilated function, and vice versa. So these two operators are nicely paired by duality. So they're adjoint of each other, and so we can use the same thing now. We know that for convolution, you should think of S0 because it's L1, which is a nice convolution algebra. This is L1 norm preservation. The stretching operator with this ST is compatible with dilation. So stretching a convolution product means stretching both factors. Whereas the D operator is good enough, is good for the pointwise multiplication. Now we even have seen that the Fourier transform maps convolution into pointwise multiplication. So in the Fourier algebra, we should use the dB operator, whereas in the bounded measures or so, you should use this. Okay, now, if you're looking at such an expression and you're doing it in a naive way, but you can build a proof on this, I don't go through the details, then you would say, oh yes, this is great. The delta function has area 1, it's a decent function. If you compress it, you let b go to 0. I think there I should rewrite everything. It should be the STA and DA. Yeah, so because I have to compress this, it will go to the delta 0. But what is the Fourier transform of this here? Well, the Fourier transform of a dilated Dirac comb is the compressed STB of the Dirac comb, which means you're doing an area-preserving stretching of a Dirac comb. Well, think of yourself, you have a Dirac comb, and somebody is starting to stretch the time axis. So the observer will be a test function. You can take it with compact support, maybe in the interval from -10 to +10. But the Diracs are moving away, so the central Dirac is staying, is remaining. Okay, sorry, yeah, okay. I'm talking about the S0 effect on the Dirac comb, and they go to just the Dirac measure. Now, the dB, as I said, is the Fourier transform of the Poisson of the Dirac comb, and the Dirac comb under the Fourier transform is the Dirac comb. So the dB of the SHA must go to the Fourier transform of the Dirac. So once more, ST stretching a Dirac comb by moving the points in the mass-preserving way to infinity gives us a limit delta 0. Only this one is observed anymore. And that's exactly what we do when you say, I'm periodizing and making the period arbitrarily large. Well, this is a standard trick to derive the Fourier transform. Here we are saying, no, we are living inside of S0. Everything is perfectly well defined, but the observer who is watching locally doesn't see this periodic repetition if they are in the distant future or so. So kind of, if you think of mankind or so, and if you would assume that everything is repeating after 20 million years, you will still live as if it was only now. So, okay, maybe a stupid comment. Now the Fourier transform of Dirac comb is Dirac comb, and ST goes to dB. So this will go to constant 1. That was in short. So if you combine these two convergent things, it will go to 1 times f multiplicative, which is f, times delta 0. Of course, you have to make sure that, that's the difficult part of the proof, that if you're doing this in a coherent way, I did here a limit on this first and then a limit here, but if you do it in a synchronized way, that it's still okay, but well, let me do it this way. Okay, so we are using, I would like to use this fact I wanted to use this fact to tell you what's going on. Now, I would like to jump further. Yeah, maybe I will mention a few things which we have done recently in the last course, because I have also some MATLAB things to be for the second part. So in the world of the Banach-Gelfand triple, we can not only deal with signals and functions and generalized functions, mild distributions and so on, but we can also use this idea for operators. So very often people are talking about operators from L2 to L2, from L1 to L1. Actually, I'm currently writing up a proof of Vandal's theorem, which says every translation invariant operator from L1 to L1 is a convolution operator with bounded measures. Well, will my proof go, which is known as Vandal's theorem? Well, I will say if you take the operator, which is an abstract operator from L1 to L1, I can take the dual operator. That dual operator certainly maps the dual of L1 to L1, but I don't know what the dual is, so I will be able to restrict it to the bounded continuous measures. So I will find out that this adjoint operator will map C0, which is part of the dual space of L1, into the bounded continuous functions. But then we are in the situation of the original proof that we gave. So it must be a convolution operator with a bounded measure. Now, this is the characterization of the joint mapping. So with some further argument, I will argue that the joint of the joint is the original one, at least, or extends the original one, and then we are having this. But there's a flip by the adjointness relation, but we know that with every measure, also the adjoint measure, the flipped measure, is also a bounded measure of the same norm. So I will try to write down a proof and put it into the script of Vandal's theorem based on the modification of our original first proof combined with the adjointness considerations. But as I said, trying to avoid measure theory and the concrete realization of the dual space as L infinity, the space of bounded continuous functions. Essentially bounded measurable functions. Sorry, I have to do the correction or so. Now, in this world of operators, we have now a Hilbert space of operators, which people have called the Hilbert-Schmidt operators. And it's a classical topic which you find in many books in functional analysis in the late chapters. And probably you find the fact that such compact operators have, if they are symmetric, they have a spectral resolution or a spectral representation. Now, this is the analog of the linear algebra fact that every symmetric matrix or every normal matrix, so every matrix which is equal to its complex conjugate, transpose conjugate, so in MATLAB, every matrix with A equals A prime, or at least A commutes with A prime, then it's a normal matrix, has a representation in an orthonormal basis. So this is usually called a Hauptachsen transformation or main component decomposition. It's a very useful tool. And Hilbert-Schmidt operators are essentially those operators which have such a diagonal representation with L2 coefficients. So that's the natural thing. Trace class operators are the ones with L1 singular values, and the dual space is all the bounded operators which have all the compact operators which corresponds more or less to L infinity, and the compact operators inside correspond to C0. Now, there is something like the analog of Fourier series expansion now for operators. So I was telling you that we have the spreading representation. So every operator has a spreading representation. And the good thing is that the spreading representation behaves, and I was showing a MATLAB experiment, behaves like a multiplication, behaves nicely under time frequency shifts. So if you conjugate your operator t with time frequency shifts pi lambda, so that's a time shift frequency shift, then you get a new operator. And it turned out that the spreading representation of such a new operator is just a plane wave multiplied with the spreading symbol of the original matrix. Now, multiplication with plane waves in a two-dimensional setting is nothing else but doing a Fourier transform, or doing a shift with a certain parameter in the time domain. So let's say it once more. We know that if you shift a function on the time side, it will result in a modulation with the conjugate frequency on the Fourier transform side. And if you multiply with the pure frequency on the time side, it's a frequency shift, so it goes to a shift in the frequency domain. Now, this is why it's better to take not this spreading function, which I called eta, but to take the Kohn-Nirenberg symbol, which is the symplectic Fourier transform of this. This is just to correct for minus and so on, but it's essentially a two-dimensional Fourier transform. And then it's just a shift. So that's a very important fact. So conjugation is this. Now, what was the interpretation of the frame operator for a Garber family? We're adding up all the projection operators on all our Garber atoms. How do we get the Garber atom? We move the Garber, the original Gauss function, let's say, by a time frequency shift operator. Then we do the projection, and then we're going back. But so we can say that all these projections onto the atoms are obtained by the one single projection of the operator on our atom. Okay, so therefore we have a collection of shifted questions for the Kohn-Nirenberg symbol. I will show you this and recall this again about the story. Now, one more thing has to be mentioned, namely the eta of the PG, that's the symbol for our spreading function, is not a new object in a way, but it's just the autocorrelation of the window by itself. So it's the BGG, the short-time Fourier transform, where the window and the signal are the same as a function of the time frequency plane. So you have this property. And so most of the time we would use a situation where we have decent while decaying and smooth functions. Therefore, this is a function which will have good concentration. We usually take the L1, now the L2 norm of G equal to 1. That means G, it's BGG at 0, which is G against identity operator to G. So this is G with G, which is square of this. I'm not sure I didn't put it here now. Then we see that this BGG has a peak at origin at 0. And the good quality properties, meaning smoothness and decay give good representation formula, give good properties. Now, what we are doing here when we do the Garber frame operator, we're summing up over all these time frequency shifts where lambda is now going through a lattice. So what does it mean? We're summing up over a lattice of all the shifted things of some nice object. Actually, I should mention maybe beforehand, if you start with a G in S0, it turns out that BGG is in S0 of two variables or 2D variables. Even the converse is true. So you can characterize S0 in a nonlinear way. It's a quite surprising fact, but we don't use it anymore. That you can define S0 by saying, I take all the functions in L2 which have this here in L1. I could also say I take all these functions where this is in the Wiener algebra. That would be the same thing, but that's just playing around with symbols at the moment. So what are we doing when we are doing a sum over these symbols? We would say, okay, this is just a special case of periodizing a given function. So again, if G is a nice atom in S0, this sigma t will be a descent function of two variables, a bump function. Actually, if you start with the Gauss function, this will be having the shape, at least the absolute value of this symbol and also of the eta. They both have a shape of a Gaussian. So you're talking, I'm in the Koenig-Berg symbol, I'm just periodizing a bump function. And we have seen in the discussion of Poisson's formula that periodizing a function means just sampling on the Fourier transform side. So this is kind of one of the important questions that I would like to tell you. So formula 493, the Garber frame operator is the operator which plays the significant role in doing Garber expansion, is the operator, in my terminology, which uses the given redundant Garber family, as we know, as if it was an orthonormal system. So we are taking coefficients with respect to the family and using this as coefficients for atoms. But this is exactly because we have normalized elements. So G has L2 norm 1 is here. Therefore, also G lambda has the same norms. Therefore, it's just the orthogonal projection, the best approximation of a scalar multiple of G lambda by to the given function f. So we are summing up over all these projections. And I was telling you, these projections are just the projections onto the original atom moved around. Now, if we go to the time frequency, now to the here you see the details, I'll leave it out. If you go to the Koenig-Berg symbol, you're getting the sum of shifted versions of the Koenig-Berg symbol of this projection operator. And I told you, the projection operator is nice. Therefore, the Koenig-Berg symbol, the spreading function, they're all in a zero. That's where all these nice invariance properties come in. So this line is the verification that it's really the same to move the projection operator around or to just project onto this G lambda. So this is a short commutation. But then we know that we can do a periodic function can be expanded and we can also rewrite it back. So I'm just saying eta is, we go to the spreading domain and then we go back to the inverse spreading domain, but I'll leave it out here. So the final result is, and you may remember that the Poisson formula requires to go from a lattice to the adjoint lattice. Now I also suggested to take the symplectic Fourier transform instead of the ordinary Fourier transform. And that's why we don't get L perp, this orthogonal lattice, but we get L circle, which is called the adjoint lattice. When you start with a lattice of the form A and B in the discrete setting, you get the lattice with lattice constants n over B, n over A. So the orthogonal lattice would be just the lattice with n over A, n over B, keeping the order and taking the complementary divisor of n, whereas now we are doing the complementary, but we change the role of time and frequency. This is due to the fact that we have this as part of the symplectic Fourier transform. The symplectic Fourier transform is not like the Fourier transform of order 4, so you have to apply it twice to get the flip operator and 4 times to get back to the identity. Now it's even better, only twice applying a symplectic Fourier transform is giving you this. But there is a very nice and very important interpretation also of this adjoint group. It's exactly the set of all time frequency shifts which is commuting with the original ones. So you could say, well, these are the compatible time frequency shifts. So what is the interpretation of the Fourier transform, the transition from ordinary Fourier transform to Fourier series? We're saying first I have the Fourier transform for ordinary functions and so on, but then I'm coming with a periodic function. Which of the frequencies do I need for a representation? And the answer is just take those which are compatible with the periodicity. If you have alpha periodic functions, you can use the functions which are alpha periodic, which means the pure frequencies with parameter 2 pi over parameter over alpha. So 1 over alpha is the key. So that's the orthogonal lattice. And so here you have the same thing. you're saying every operator in discrete setting would be written as a superposition of these pi L's. But now the SG lambda is obviously a periodic thing. It is obtained by periodization of an original one, so it's a periodic thing. So you don't need everything, but only those which are living on the adjoint lattice. So these pi lambda 0 are exactly those which are commuting with the original one. So the inversion theorem actually is a nice thing. You would say, well, in the finite dimensional case, I could do it, and I could say, okay, if I take the full group lambda, all time frequency shift, n squared time frequency shifts, what is the lambda 0 then? Well, a matrix which commutes with all the time frequency shifts is periodic with period 1. Well, that means it's constant along side diagonals, but also its Fourier transform is periodic with period 1, or all the side diagonals have to be 0. Well, it's the identity operator, maybe with a factor or so. So here we have a more interesting situation. We're saying if we choose a lattice which is having some redundancy, like our case 3/2, we will have another lattice which has the inverse redundancy. So it's 2/3 of 480 elements. It's the frequency space. It's the time frequency lattice which has A rows and B columns. So I'm expressing the fact that the parameters in time is n over b, and in frequency is n over a in a different way. And the other thing is, well, what are the coefficients? And we have seen in the Poisson formula, if you periodize a function, you just take the continuous Fourier transform and you sample on the lattice, on the orthogonal lattice. So I've just mentioned here that the spreading function this here, the spreading function of the original building block is just the short-time Fourier transform, and so the BGG actually, the autocorrelation, and therefore you have to take the BGG and sample it at the adjoint lattice. So this is a very important formula and gives you a lot of structure, and actually it's valid not only for separable lattices, but also for oblique lattices also. So this formula has been extremely useful for the derivation of results, saying when is such a family of a Garber family along a lattice lambda in the time frequency plane, when is it certainly a Garber frame? And the answer is this inversion trick, which I was explaining in the context of discrete convolution. I would say, well, if the sum of these values is less than 2, then we're fine off. Well, why is this true? Because due to our normalization, the BGG at 0, 0, I mentioned already, is just the norm of g squared, which is 1. So if the total sum of all these absolute values is less than 2, it means the non-zero terms are at most like this. Well, that means that in this representation, we have, if you pull out the C lambda, this operator here is invertible because it's identity plus something which is strictly smaller than identity. How do you invert it? You write the infinite geometric series. So the remaining terms, you're writing a sum from power 0 of this remaining sum to power infinity. So you're taking the square of maybe of this sum, but with the pi lambda 0. You're taking this, so you're writing a simple geometric series, and this is a well-defined operator. Actually, it's not only a well-defined operator on L2, but it's even an operator which is on any LP space, on any on S0, for example. Yeah, you see here, the difference is small enough, and so you can invert it. What is the consequence of this? Well, that the dual atom, which I have shown you in MATLAB, which is obtained by inverting this operator, so this is now legitimate, it's guaranteed to exist, will be in the space S0 because this series of, infinite series of these operators will be like this. Of course, it still means that you have to look for different ways of computing this, and let me see what else, but I think I have to go to the break. Yeah, okay, I think it's a good moment to take a stop and to come back to you maybe after, I don't know, 6 or 7 minutes, I would suggest, because I have still a lot of material.